Okay, so we've got catapult that launches a 50-kilogram rock at a speed of 29 meters per second. If the catapult was drawn back 3 meters, how much force was used? What kind of question is this? Okay, kinetic energy is changing, but what kind of question is it? Law of conservation of energy or work energy theorem? Work energy theorem. Okay, how do we know that? What's changing? Energy. What doesn't change in a law of conservation of energy question? Energy. Okay, that's how we can tell the difference. Always look for that. Okay, it's kind of a simple thing, but it's sometimes not as easy to see in a question. All right. Okay. So for question number 1, give them a mark for their givens. Okay, their givens were the mass, 50 kilograms, final speed, 29, the initial speed would be 0, okay, and the distance that the catapult was drawn back is 3 meters. All right, so next mark, recognizing it's a work energy theorem question. Work is a change in energy, all right, or maybe they wrote force times distance is EF minus EI, either one is fine. Okay, next mark, plugging in that this was a change in kinetic energy. So force times distance equals 1/2 mv squared. Or maybe they wrote it was EK up here, as long as they showed somewhere that it was kinetic energy that was changing. All right, our initial kinetic energy here is shown to be 0, okay, because when it's in the catapult, it's not moving, so it has no kinetic energy. All right, I'm trying to find the force, so what do I have to do with distance? Divide it over to the other side. So we're going to end up with this. That's their next mark. Okay, for 1/2 mvf squared divided by d, or maybe they went straight to plugging in the numbers. Okay, whichever is fine. And then for our 5th and final mark, we should get 7,008.3. Sorry, I don't have 2 decimal places there. I should, but 7,008.3 newtons. Make sure that the units are right. It does have to be newtons because we were calculating force. All right. Questions on number 1. Is that a lot of force? Yes. That's why lots of times they had horses that did that job. Catapults were very hard to load, and they have lots of pulleys and force multipliers and things like that that help you load them. Okay. All right. Number 2. Okay, once again, marks for givens. Okay, we're looking for the height that a rocket will reach if a force of 200 newtons is exerted on it for 4.5 meters. All right, so there's our givens there. All right, what kind of energy is changing in this one? Potential. At least that's in the end what we're looking for. Is kinetic energy changing at the beginning of this? It is, okay, but that's not what the question's asking about. All right, so give them a mark if they got works of change in energy. Okay, something about EP and EP final and EP initial, something like that. Okay, next mark is for manipulating the formula to solve for the final height. Okay, so we've got force times distance, which we were given in the question. Okay, is equal to m times g times hf, because obviously catapults sit on the ground where the height is 0. Okay, so we have no initial potential energy. So we divide both sides by m times g, and that'll leave us with hf. So we're up to 3 marks here to this point. Okay, mark for plugging in numbers here. Okay, so give them a mark if they plugged in the numbers correctly, because we're short a mark there somewhere. And then the final answer is that it should reach a height of 367 meters. Questions on number 2. Okay. Those 2 questions were on a unit exam about 4 years ago. That's where I took them from. A unit exam I don't use anymore. Okay? Give you an idea of how hard the work energy theorem questions on the unit exam will be. They'll be just like that. Okay? Okay. So here's the situation. Toboggan going down the hill. No, it's not a candy cane on a triangle. Okay, I know I can't draw, but it's toboggan going down a hill. Okay, all right. We know the initial height is 30 meters, okay, and we know that the initial speed is 14 meters per second, right? We know that a little while later it's going faster, and the only way it's going faster is if it's a little further down the hill. Agreed? All right, so we're looking for the second height, or the final height here. Is there any work being done between this spot and this spot? No. So the energy is staying same. All right, so then we can start out with this. Okay, EI equals EF, and we have both kinds of energy at both locations. At least we think we do. It's possible that this could come out to 0, but it's highly unlikely. Agreed? Even if it does come out to 0, we still need to solve for that. It's not going to come out to 0. Okay? All right. So we've got initially then both kinds of energy. Okay? mghi plus 1/2 mvi squared equals mghf plus 1/2 mvf squared. Right? We got all, none of those are 0, so we got to keep them all. What can I get rid of? Mass, which is good because they didn't tell me what it was. I could make up a number, but I don't want to. I want to enter less stuff into my calculator, okay, and just eliminate mass since everything's being multiplied by it anyway. Okay, I need to get HF by itself. So what do I have to do with the 1/2 VF squared? Since I'm adding it right now. Subtract it, yeah, right? I mean, essentially then what I'm doing is going mechanical energy, that's this, minus kinetic energy equals potential energy. Isn't that what we worked on the last couple of days, right? That's how we calculate mechanical energy, kinetic plus potential. All right, so that's what we're going to have. We're going to have GHI plus 1/2 VI squared minus 1/2 VF squared equals GHF. All right, I want HF by itself. What else do I have to move? The gravity. How do I do that? Divide it. Right. Okay, it does not cancel the G on the top. Okay, it would have to be in every term for that to work. It's not going to happen. Can I plug everything in now? Right, I'm at that stage. Okay. So 9.81 times 30 plus 1/2 times 14 squared. So there's my initial potential, my initial kinetic, minus my final kinetic, 1/2 times 23 squared, divided by 9.81 should give me HF. All right, so we'll plug all that in. Okay, so 9.81 times 30 plus 0.5 times 14 squared minus 0.5 times 23 squared divided by 9.81. All right, so we're 13.03 meters above the bottom of the hill. Okay, so the one we did at the end of the day yesterday, that would be the one with the roller coaster. Okay, and this one, that is exactly like what we would get on a unit exam. Okay, in fact, once in a while, I make it so that actually one of the forms of energy is 0. Okay, like I might have said instead on a question like this on an exam, calculate the speed at the bottom of the hill. All right, so I would have given you, yes, there's 14 meters per second and 30 meters here. Okay, but then I would have said it's at the bottom of the hill. So at the bottom of the hill, it only has kinetic energy, no potential energy, so something like that. Okay, but that's the hardest math that you'll have to do with that. Okay, there's a lot of stuff to move around, but it's always the same. And it doesn't matter what kind of conservation of energy question you have, it's always the same math. All right, is this starting to make a little bit more sense? Okay, we're going to practice this. We're going to work on this today. Tomorrow we'll do our unit exam review. Monday we'll work on energy again. Sorry, on Monday we'll do efficiency. And then Tuesday we'll do our energy conversion lab, and then Wednesday is your test. Okay, so it's coming right up. Alrighty? All right. What's that? Probably on Friday. Yeah. Okay. Any other questions on this one? All right. Try that one. This is kind of like the one I was telling you about where it would be hitting the ground, okay? But it would have both at the beginning. Okay, so in this question, here's our situation. Cliff. Ah! Like that, okay? So we've got the car moving off of here at 25 meters per second. I'm not even going to attempt to draw a car. Okay, so you'll just laugh at me, and I'm just not in the mood for that. Okay, moving at 25 meters per second. When it strikes the ground, it's moving at 53 meters per second. Okay, what we don't know is how tall the cliff is. Any work being done in between the top of the cliff and the bottom of the cliff? No, but a lot being done at the bottom of the cliff. Okay, the shape of the car will be radically altered. That's work. Okay, I hope so. They didn't mention it, and they didn't give the mass, so no details, and that we'll just assume. Okay, maybe it was like in, if you've ever seen Rebel Without a Cause, it's like this incredibly ancient movie, okay, with James Dean, and they play this game of chicken. Not the kind of chicken where you drive towards each other, but a game of chicken where you drive towards a cliff, and the first person to jump out of the car is a chicken. Which really seems stupid, because you're going to wreck your car one way or the other. Anyway, yeah, so they both, there's no one in James Dean's car. He was the chicken. The other guy got his leather jacket caught on the, cars used to have these things that would roll the windows down. He gets his leather coat caught on that, and he can't get out of the car. So, yeah. What was the point I was trying to make? Whatever. Okay, so we got EI equals EF. Okay, we have obviously at the beginning potential energy. We have at the beginning kinetic energy. But at the end we only have kinetic because it's going to be at the bottom of the cliff where the height is 0. Okay, I'm looking for the initial height because that would be the height of the cliff. So what do I need to do with this? Subtract it over to the other side. Okay, so I'm going to have m times g times hi equals 1/2 mvf squared minus 1/2 mvi squared. What can I do right now? Take out the m's because they didn't tell me what it was anyway. Now what do I do? Divide by g. All right, so the initial height of the cliff is going to be 1/2 times 53 squared minus 1/2 times 25 squared divided by 9.81. That's a big cliff. Okay, 111 meters. Okay, questions on that one? Starting to get it? Okay, are they all pretty much the same? Yeah, okay, they are. Once you get kind of the pattern, then they're all pretty easy because they all work the same way. Okay. Okay, let's try that one as our last law of conservation of energy question example. Okay, so if you jump out of a plane, then there's no work being done, assuming that there's no air resistance, which there is, but we're going to work in the perfect utopian physical world. Okay, so this is definitely an EI equals EF type of a question, right? And for law of conservation of energy, it doesn't matter which direction you're going. Okay, like when you jump out of a plane, you don't have any vertical velocity, but you move at the same speed as the plane. Okay, like in the perfect physical world, if there was no air resistance, you would jump out of a plane and keep moving along at the same speed as the plane. Okay, I mean, yes, you would fall down away from it, but you would stay with it. Okay, the difference is that when you jump out of a plane, immediately you start slowing down because of air resistance and you fall down and behind the plane. Okay, but in the perfect physical world, you would jump out of the plane. I have to draw a plane, a stick plane. It's a stick plane. Oh god, then I ruined it. Okay, so if you jumped out of a plane, okay, you and the plane would keep moving along at the same speed. So it would go this way and you would go this way, but you would still horizontally be moving exactly the same. Okay, it's kind of weird, but that's what would happen in the perfect physical world. Obviously in the real world, as soon as you jump out of the plane, the air hits you and you start falling behind the plane because the plane can move faster and it's powered, right? You're not powered and it is. Everybody with me there? Okay. So, what I'm trying to say here is that your speed jumping out of the plane doesn't matter whether it's vertical or horizontal. It still contributes to your energy, doesn't it? Okay, you still have some speed, so you still have some kinetic energy. All right, so we've got both kinds at the beginning and both kinds at the end. So mghi plus 1/2 mvi squared equals mghf plus 1/2 mvf squared. We can cancel the m's right away. Okay, we don't need them since they didn't tell us it anyway. I'm trying to solve for this. So what do I need to move first? mgh. Well, actually just gh now. Okay, and how do I move it? Subtracting it. All right, so ghi plus 1/2 vi squared minus ghi equals 1/2 vf squared. What do I do with the half? Divide. And then square root. All right, so if I plug in my numbers, 9.81 times 10,000 plus 1/2 times 90 squared, okay, minus 9.81 times 8,000 over 1/2. Okay, so 9.81 times. Whoop. Okay. Minus. Okay. 2, 3, 6, 7. All right. Fast? Very. Okay? Very, very fast. And I can remember somebody the other day tried doing this high altitude jump where they achieved a speed that was faster than that, okay? Kind of wearing a special suit and helmet and things like that. There's kind of a top speed you could reach as a human being, okay? Because when you get too close to the speed of sound, there are problems, okay? That whole sound barrier thing, yeah, probably not going to withstand hitting that, okay, as a human being. An aircraft can withstand it because of the design and shape and that they've got power, okay, but unlikely for a human being to withstand breaking the sound barrier without being inside a plane when it happened. He did that at high altitude, right? So again, he would have been above, he would have been where there was a lot less air. So the speed of sound is a lot lower. Yeah. Yeah. If you're doing this at around sea level, it's a much bigger deal, right? Okay. You don't want to go that fast. You can't actually really. I mean, under normal conditions, you can't really go that fast. Under perfect conditions like these, like the Red Bull guy and this latest one, under those kind of conditions at extremely high altitudes where there's very little air resistance, then yes. Okay, but below that in kind of normal air, can't do it. All right. Everyone getting a little more comfortable with that? Okay, so I gave to you here just a few minutes ago a worksheet that's got some work energy theorem stuff on it. It's got some potential and some kinetic energy stuff on it. And then at the bottom, it's got conservation of energy questions. And then on the back side, there's a little bit more energy stuff that you can use kind of as review activities if you want to for your unit exam. You are also going to get a review package for that tomorrow. All right, so what I want you working on right now is that sheet. Kira, which question was that with the shot putter? 7. Okay, question number 7 on the first side, guys, is really poorly worded, and I can't even remember right now. Okay, I've got something written here on there. So this, it says a shot putter puts a shot that has a weight of 71.1 newtons. Okay, what's weight again? Which force? No, kilograms isn't weight. Kilograms is mass. Weight is newtons. Weight is the force of gravity. Okay, and if you recall, we calculate that by going Fg equals m times g. So if they just given you here what m times g equals, have they saved you a little bit of work? Yeah. Okay. So you just need to determine the change in potential energy. So really you need to determine the potential energy at the ground and the potential energy here, and then the potential energy here at 2.13 meters, okay, and you'll get your answers. One of these numbers is measured from the ground, and one of them is, so this would be, I think this is the one that's the change in energy from the ground to 2.13 meters, and this one is the change in energy from 1.52 meters to 2.13 meters, because the question doesn't specify. It doesn't say calculate the change in energy from the ground to 2.13 or how much work the shot putter did in putting it from 1.52 to 2.13. It's not, it doesn't specify. So there's two ways for you to interpret that question, and these are the two answers you would get depending on which way you interpret it. Okay? All right, so have a go at that, and if there's questions, we'll go through them together. Okay, so back to this thing with the airplane, where when you jump out of the airplane, it doesn't matter which direction you're going. Okay, your kinetic energy, when it says 1/2 mv squared, that v isn't velocity. That v is speed. Speed is scalar or vector? Scalar. Energy is scalar, work is scalar. Okay? If you have 2,000 joules of energy, you have the potential to do 2,000 joules worth of work in whatever direction you please. Okay? So when we did those, even the toboggan question, okay, where we had the toboggan going down the hill, this velocity here, whatever it had, I think it was started out at 14 meters per second, is it straight down? It's not. It's angled, right? When we did the roller coaster question, okay, and I had the roller coaster cart at the top here, and I said it was moving at 5 meters per second. It wasn't moving at 5 meters per second down. It was moving 5 meters per second that way. Okay? It doesn't matter which way you're going. If you're moving, you have kinetic energy. Okay? Irregardless of what direction you're going. Does that make sense to everybody? Okay, you know what, guys? Forget about number 7. I just keep reading that question, and I like it less and less every time I read it. It's just worded so poorly. I got to look at a way of rewording that. Okay, so don't even do number 7. Just every time I read it, it makes less and less sense. Okay, so don't do that one.